Imagine this traveller of the silent cosmos arriving here not by chance, but as if something in the dark reached out and guided you. Behind the sun, an ancient object drifts in silence, following a 1 in 20,000 path that brushed past 3 wandering worlds. What if such precision isn't coincidence? What are the odds that a fragment of another star would slip into our system, vanish in the sun's glare and move as though it remembers where it's going? A light that blinked once and disappeared. A whisper hidden in the radiation between planets. And now the mystery waits for us to notice, to listen, to wonder. Stay a while, traveller. Traveller, tonight the universe opens quietly, the way a faint star becomes visible only when you stop trying to see it directly. Somewhere in the dark of July 1st, 2025, the Atlas telescope in Rio Hurtado, Chile, one of 4 silent guardians meant to watch for dangers, drifting toward Earth, captured a point of light. That is how all cosmic stories begin, not with alarm, not with revelation, but with a tiny movement against the stillness. Atlas, the asteroid terrestrial impact. Last alert system was never designed to find visitors from other stars. Its purpose is earthbound to detect objects that might one day cross our path too closely. 4 telescopes. Hawaii, Chile, South Africa, scanning every clear night, taking repeated images of the same sky, comparing them pixel by pixel, listening for anything that shifts even slightly. Most detections are ordinary small rocks, harmless wanderers, the quiet debris of creation. But sometimes in the soft hum of the system, something moves differently. On that night, one object drifted across Atlas's field of vision. This alone was nothing unusual. Everything in space moves. Nothing is ever truly still. But when the algorithms calculated its speed, the numbers carried a whisper of strangeness. Out near Jupiter's orbit, far from the fierce pull of the Sun, where motion should be calm, the object was racing at 58 kilometers per second. Earth travels at 30 km, Mercury tightly bound to heat, and gravity at 48 km. But this light was moving faster than anything that belonged to our Sun. Astronomers examined the orbit more closely. They traced its path backward through time, expecting the familiar ellipses that tie our solar system together. But instead of looping curves, the calculations revealed an open hyperbola, the unmistakable signature of a body not bound to our star. Objects like this do not come home. They do not return. They pass through untouched by the Sun's gravity, carrying with them the cold memory of another system. The next day, July 2nd, 2025, the object received its title 3 Atlas, the 3rd confirmed interstellar visitor in the history of human observation. This designation is not given lightly. In the entire span of astronomy, in all the nights we have studied the sky, only 2 other known objects have drifted into our solar system from the deep galactic dark. The first was Oumuamua in 2017, a thin tumbling shard with no coma and a peculiar acceleration as it left the inner solar system like a breath exhaled too softly to trace. The second was 2I Borisov in 2019, a more familiar comforting comet rich in water vapour and carbon monoxide. And now, Thruyatin Atlas, larger by far than either one, older than both, and walking a path that did not echo the others. Unlike Oumuamua, which approached from above the solar system's plane, and unlike Borisov, which arrived from Cassiopeia at a steep angle, 3 Atlas came almost perfectly aligned with the ecliptic, just 4.9 degrees off the orbital plane where Earth and all neighbouring planets circle the Sun. The probability of such alignment occurring randomly is less than 0.2%. Not impossible. Nothing in the galaxy is impossible, but rare enough that astronomers whispered quietly among themselves as they checked the numbers again. Its trajectory carried more curiosities. On October 3rd, 2025, it passed within 29 million kilometers of Mars, closer than any known interstellar object has come to a planet. In March 2026, it is expected to pass 54 million kilometers from Jupiter. The odds of a random interstellar body drifting close to multiple planets in a single passage is 0.05%, small enough to feel like coincidence layered upon coincidence, though the universe often arranges its events through improbable chains. and yet observer the cosmos is vast. Rare events are abundant on galactic scales. What astonishes us might be commonplace in the long quiet between stars. As 3i Atlas continued inward, astronomers watched its brightness, its spectra, its subtle changes. Hubble observed a visible coma forming at 4 AU far beyond Mars, too early for solar heat to awaken ordinary comets. JWST detected carbon dioxide dominating water vapour at an 8:1 ratio, suggesting origins colder than any region of our solar system. Later, the Very Large Telescope captured nickel vapour 4 grams per second, with iron initially absent an odd chemical signature that raised questions but not conclusions. Nature often behaves in ways we have not yet catalogued, especially an object that may have travelled for 7 to 10 billion years shaped by cold older than Earth. Through it all, its orbit remained unperturbed. No accelerations beyond gravitational expectations, no deviations, just a steady descent toward the Sun. Then came the challenge no observer could escape perihelion on October the 29th, 2025 at 1:36 AU, just inside Mars's orbit precisely when Earth would be positioned on the opposite side of the Sun, the visitor's moment of greatest activity when ancient layers would crack, when ices would erupt, when chemistry would speak, would unfold entirely hidden behind solar glare. Not conspiracy, not intention, just the geometry of orbits, the quiet indifference of celestial mechanics. And so on the last night before the object slipped into the Sun's blinding light, the telescopes gathered what they could: position brightness spectra, the faint whisper of its tail. Then they waited, and so do we. Tonight, listener, let this truth settle softly. Some mysteries reveal themselves only after they have passed through fire. Some visitors speak only when they return to the cold. And it is all right, truly all right, not to know yet. Sleep now. The cosmos keeps watch. Traveller to understand 3i Atlas, we must look gently backward the way an astronomer rewinds the motion of a comet across the sky to find where its long story began. Interstellar objects are rare in our observations, not because they are rare in the galaxy, but because our eyes have only recently grown sensitive enough to notice them. For most of human history, we slept beneath a sky filled with wanderers we never knew were passing. Only in the last decade have we truly begun to listen. Before 3 Atlas, only 2 confirmed visitors drifted into our solar system from the deep ancient dark. Their names, Oumuamua and 2i Borisov, already feel like early chapters of a cosmic book we have just opened. Their stories are brief, almost fragile, but they change the way we think about our place in the galaxy. Tonight, observer, let us walk softly through those memories. The first visitor arrived on October 19, 2017, detected by the Pan-STARRS telescope in Hawaii. It was small, faint, and moving strangely fast toward the inner solar system. When astronomers traced its orbit backward, they found something unprecedented. It was not from our Sun. Not from the Oort cloud, not from the Kuiper belt, not from any gravitational family we recognized. It had slipped in from the emptiness between stars, a traveller on a hyperbolic path. They named it Oumuamua, a Hawaiian word meaning scout messenger, or the first to reach out. And perhaps in a poetic sense, that is exactly what it was. Over the weeks that followed, telescopes across the world turned toward the object. But light is a fragile thing when a body is small and distant. We learned what we could. It was elongated, perhaps 200 to 400 meters at its longest dimension. It tumbled oddly, not spinning like a solid body should. It had no coma, no tail, no visible outgassing, behaving unlike any comet we had seen. Then, as it drifted away from the Sun, it accelerated. Very slightly. Too slightly to shout, but enough to whisper. Enough to make the instruments pause. Most scientists attributed the motion to non-gravitational forces, perhaps outgassing too faint to detect. But not all were convinced. Harvard astrophysicist Avi Loeb suggested it might be something more, a technological artifact, a solar sail, pushed by sunlight, a fragment of something artificial. Controversial, yes, but questions in science often begin with discomfort. Still no signal was detected, no structure was seen. Oumuamua left our system as quietly as it arrived, accelerating gently into the dark, offering only mysteries and the echo of possibilities. 2 years later, in August 2019, the universe whispered again. But this time, the voice came not from a high-tech observatory, but from a small telescope built by an amateur astronomer, Gennady Borisov, in Crimea. He spotted an object that behaved almost exactly like the comets. We know a bright coma, a dust tail, volatile emissions. Its composition, water vapor, carbon monoxide, organic molecules, felt familiar. 2I, Borisov was reassuring. A reminder that not all interstellar objects are strange. Some are simply comets flung from another star during the birth of their planetary system. A reminder that the galaxy is full of worlds forming, colliding, ejecting their icy seeds into the void. Yet even Borisov was not ordinary. Its carbon monoxide levels were unusually high, far higher than typical solar system comets. This suggested a birth environment colder, more extreme than anything near our sun. Another quiet indication that the galaxy is richer and stranger than our local neighbourhood implies. These two visitors formed a pattern, a small sample, but enough to expand our imagination. Enough to remind us that our solar system is not the standard template for planetary systems, but only one of countless variations. Then came 3I Atlas, arriving not from above or below the ecliptic like the others, but aligned almost perfectly with the flat disk where our planets orbit. Moving faster, larger by far, more active at greater distances. Chemically stranger, trajectory more statistically improbable, not suspicious, just different. Tonight, listener, think of the three objects together as pages in a book the galaxy has only just begun to let us read. Oumuamua, silent, dry, accelerating. Borisov, icy, active, familiar yet extreme. Atlas, large, volatile, rich, ancient, unusually aligned. 3 chapters, 3 stories, 3 glimpses into planetary nurseries we will never see. Each object a memory torn from a different star and sent drifting into the dark. Each one older than humanity, older than our planet, older than our sun. When scientists line the 3 trajectories together on a map of the sky, each arrives from a different direction as if drawn from distant regions of the Milky Way. None show signs of common origin, none suggest coordination. They are simply wanderers following the physics of their birth, the long drift of interstellar space, and the quiet pull of our sun. And yet the arrival of 3 such visitors in less than a decade tells us something profound. Not that they are rare, but that our instruments were once too blind to notice them. The galaxy has always been filled with these icy messengers. We are only now learning to see them. Traveller. This is the beauty of it. We are not alone, not because we have found life, but because we are surrounded by the remnants of countless worlds. Because stones from other suns now glide past ours. Because the galaxy is speaking in ice and dust and motion. It's all right to not understand everything at once. Some mysteries drift into view only when the universe decides we are ready to see them. Rest now. The cosmos remembers even when we do not. Traveller, to understand 3I Atlas, we must step into the quiet geometry of the cosmos where everything moves according to ancient laws, and yet sometimes those laws arrange themselves into patterns that feel almost intentional. Not in the sense of agency, but in the sense that raw events, when observed closely, can look like a message written in numbers rather than words. When an interstellar object slips into our solar system, it can come from anywhere, above us, below us, sideways, steeply angled relative to the thin disk of planetary orbits. Space is 3-dimensional. Arrivals should be random. And yet 3 Atlas chose a path so strangely aligned with our own celestial plane that the first reaction among astronomers was not alarm, but a quiet contemplative pause. Most planets, moons and asteroids orbit the Sun within a narrow sheet called the ecliptic plane. This is the flat disk the solar system has settled into over billions of years. Comets from the distant Oort cloud plunge in from all directions, often at angles of 30, 60, even 120 degrees. Interstellar objects coming from environments entirely foreign to us have no reason to approach along our planetary highway. And yet, Atlas does. Its inclination relative to the ecliptic is just 4.889°. To an untrained ear, the number feels small but insignificant. To an astronomer, it stands out like a whisper in a silent room. The probability of a random interstellar object arriving within 5 degrees of the ecliptic plane is less than 0.2%. Not impossible, but surprisingly precise, like a coin landing on its edge. Some scientists emphasize that the Milky Way itself has a disk structure, and that many star systems orbit within that disk. Objects ejected from those systems might naturally follow paths roughly aligned with the galactic plane, which itself is broadly aligned with our ecliptic. That is a reasonable explanation, a comforting one. But even so, the alignment adds to the growing list of quiet peculiarities surrounding this visitor. As 3I Atlas travelled inward, its trajectory revealed even more soft improbabilities. On October 3, 2025, it passed within 29 million kilometres of Mars, a close planetary encounter by interstellar standards. Then projections showed another near pass on March 2026. 3I Atlas would come within 54 million kilometres of Jupiter. These distances sound large, but in astronomical terms they are encounters worth noting, especially for an object just passing through. The probability of an interstellar object randomly achieving both encounters on a single trajectory is 0.005%. Again, traveller not impossible, just unusual. Small string of cosmic coincidences woven together in a way that invites not fear but deep listening. The universe often communicates through improbabilities, and science is the art of noticing them without rushing to answers. There is another detail, one that astronomers whisper about when the observatory grows quiet. Oumuamua approached from above the ecliptic at a steep angle. Borisov came from Cassiopeia, also well above. But Atlas approaches from the side almost like a T-bone alignment against the Sun's galactic motion. Not head-on, not drifting down from the north or rising from the south, but sliding across our path, aligned with the plane of worlds, but perpendicular to our star's journey around the galaxy. This sideways arrival suggests a different history than the first two visitors. Perhaps it was ejected by a giant planet in its home system. Perhaps it drifted through gravitational eddies near the galactic core. Perhaps it wandered past other stars long before reaching ours. In astronomy, trajectories are fossils, remnants of ancient interactions written in motion rather than stone. When scientists integrate Atlas's motion backward in time, they find no parent star with certainty. This object has travelled too far for too long through a gravitational sea stirred by billions of stellar encounters. Its origin is a probability cloud spread across hundreds of light years. It is in every sense a wanderer. Still, its path through our system feels almost choreographed. Not purposeful, just beautifully improbable. It dips past Mars, touches the gravitational influence of Jupiter, slides nearly within the plane where our worlds orbit, and then arcs in toward the Sun for a brief moment of warmth before fading again into the cold. Tonight, observer, imagine its long journey. Billions of years drifting, countless close passes with foreign suns, gravitational tilts and nudges too small to remember, its path shaped not by intention but by the endless patient mathematics of celestial mechanics. There is humility in tracing such a trajectory. We want patterns, narratives, meaning. But the universe offers only motion and invites us to interpret it with care. To some, 3I Atlas's alignment and encounters felt too precise, too coordinated. To others, they were simply the inevitable outcomes of vast numbers of interstellar wanderers moving through a galaxy billions of years old. After all, if enough objects pass through our solar system across cosmic time, millions, perhaps billions, some of them will naturally trace improbable lines. A 0.2% path will still happen. A 0.005% sequence will still unfold. The universe is not finely tuned for our pattern-seeking minds. It is simply enormous, and enormity breeds coincidence. Yet even coincidences deserve attention. 3I Atlas moves with a speed of 58 kilometers, fast enough to carry the imprint of a distant past, but slow enough to let us study it as it crosses our celestial neighbourhood. Its hyperbolic orbit ensures it will not stay. Nothing about its path suggests capture. It is a visitor, not a new member of our system. Still, when we watch it move across the starfield frame by frame, there is a feeling, a quiet one, that we are witnessing something ancient, completing a journey we were never meant to see. And traveller, that feeling is enough. Not proof, not speculation, just wonder. Some mysteries are not meant to be solved, they are meant to be observed, and the universe tonight is whispering softly to those willing to listen. Rest now. More will come in time. Traveller, if trajectories are the handwriting of a comet, then chemistry is its breath. And tonight, as we drift deeper into the quiet mystery of Three-Eye Atlas, let us listen to the way this ancient traveller exhales. For in the vapour rising from its frozen skin lies a story older than our sun, older than the planets beneath your feet, older perhaps than most of the galaxy as we know it. This is not just data, not just spectra, it is memory suspended in ice. When Three-Eye Atlas was first detected, astronomers expected silence, no activity, no stirring, no signals of awakening. At 2.4 astronomical units where the sunlight is a soft whisper rather than a command, most comets sleep. Their surfaces are too cold for sublimation. Their cores remain locked tight beneath crusts sculpted by billions of winters. But on July 21, 2025, the Hubble Space Telescope saw something unexpected, the faint outline of a coma already blooming around the interstellar object like a delicate breath released too early. This early activity was the first clue that Atlas is not like the comets born in our own solar nursery. Something beneath its surface responds to heat far sooner than water ice should. Water is sluggish, it waits. But carbon dioxide CO2 awakens quickly even at great distances from the sun. And so astronomers wondered, is this object rich in CO2? Does it carry a chemical signature unlike what we consider normal? The universe answered through the James Webb Space Telescope. On August 6, 2025, Webb turned its golden mirrors toward Atlas and opened its near-infrared spectrograph, a tool so precise it can read the chemistry of worlds too faint to see with the naked eye. And the result was like opening a frozen book, written in a language we had never fully encountered before. Webb found that Atlas's coma was dominated not by water vapour, but by carbon dioxide in a ratio of 8 to 1. 8 parts CO2 for every 1 part H2O. Traveller, imagine that. In our solar system, water is the primary fabric of comets. It is abundant. It is ancient. It is the first molecule to speak when a comet warms. But Atlas tells a different story. A story from a place where water ice may have been scarce, where carbon dioxide froze first, where the temperatures were so low that even the memory of heat became rare. This chemistry points not to a region like our Kuiper Belt, but to a birthplace colder, far colder than anything near our sun. A world at the edge of another star's light, a world where CO2 snow would have fallen silently on alien ground. Yet this was not the end of the chemical puzzle. A few weeks later, in early September, the Very Large Telescope VLT in Chile detected something even stranger: nickel vapour escaping Atlas at a rate of roughly 4 grams per second. Nickel, usually tightly bound within dust grains, does not sublimate easily. It requires heat. It requires proximity to a star. And at Atlas's distance, nickel should have slept held fast by the cold. But it didn't. Even more unusual was what astronomers did not see: iron. These two metals, nickel and iron, are siblings forged together in the hearts of dying stars scattered together across planetary systems. In nearly every comet observed to date, they appear in nearly equal proportion. They rise together when heated. They evaporate together. They whisper the same story. But 3 Atlas whispered only half. Some researchers floated a possibility drawn not from astrophysics, but from chemistry known mainly on Earth: nickel tetracarbonyl NiCO4, an organometallic compound that forms when nickel meets carbon monoxide under moderate temperatures. On Earth it is produced industrially through the Mond process. But the universe is older and more inventive than our machines. With nickel-rich dust and abundant carbon monoxide around its nucleus, Atlas could form this compound naturally. And because nickel tetracarbonyl is volatile, far more volatile than iron, it would sublimate into space, while iron remained hidden, trapped deeper within unmelted grains. A strange solution, but a natural one. Still, the absence of iron raised eyebrows. It added to the growing list of small anomalies, minor quiet deviations from what we expect. Not signs of anything artificial, but signs that Atlas is old, different, formed in a place where chemistry flowed down paths we have yet to map. And then iron appeared. Later in September, telescopes began detecting it faint at first, then clearly suggesting that whatever had masked it before was no longer present. Perhaps deeper, warmer layers were exposed. Perhaps fractures opened new vents. Perhaps the earlier suppression was simply a temporary artifact of physics and temperature. In the cosmos, mysteries often resolve themselves slowly without drama. Yet even as these revelations unfolded, another surprise was waiting. Round 1. 5 AU long before solar warmth should have reached the inner layers of the object, astronomers observed a sudden, almost violent outburst of water vapour, described as equivalent to a fire hose at full force. Water typically emerges gently from comets as they warm, but here the release was abrupt, as if a sealed chamber had cracked. As if pressure had built for centuries, millennia, eons, finally finding expression. This sudden switch from CO2 dominance to heavy water outgassing told astronomers something important. 3I Atlas has layers stratified ancient complex. The CO2-rich exterior may have formed in the earliest cold days of its existence. Deeper within, water ice remained trapped, insulated, hidden. Only now, under the sun's growing influence, is that deeper ice awakening. And with it came dust carrying organic cyanide compounds, carbon-rich molecules essential to early chemical evolution. Nothing unusual, nothing alarming, just the signature of chemistry older than our solar system, preserved in darkness for billions of years. As the vapour rose, astronomers mapped its motion. Not chaotic, but structured. Not smooth, but textured, suggesting fractures, vents, and internal architecture shaped by long cosmic winters. Some fragments of Atlas may have once been warmed by other suns during close passes. Some layers may have sublimated and refroze. Some surfaces may have been cooked by radiation in interstellar space. This object is not just a comet. It is a journey frozen into form. Every molecule it releases is a timestamp. Every gas is a testimony. Every grain of nickel or cyanide is a memory from a world we will never see. And yet, traveller, it drifts before us now, close enough for our instruments to touch with light, for our telescopes to breathe in the faint signatures rising from a body older than Earth's continents, older than the ocean beneath your sky. When scientists say Atlas is 7 to 10 billion years old, they are not speculating wildly. They are reading its chemistry, the way a geologist reads sediment layers. This object may predate the sun. It may come from a star that lived and died long before ours was born. It may have wandered through multiple star systems before reaching us. It may have passed through supernova remnants, molecular clouds, and the tidal fields of the galactic arms. We will never know its full story. We will only know the thin vapour it releases as it warms. Tonight, listener, allow yourself to feel the weight of that. You're watching not just a comet, but the biography of a forgotten world. A piece of a planetary system erased by time, drifting silently across light years to reach our sun's gentle glow. Chemistry is not just data, it is intimacy, a way of touching something impossibly ancient without laying a hand upon it. The universe does not speak in words, it speaks in spectra, in ratios, in the trembling of ice under distant starlight. Let the mystery stay a mystery for now. Let the numbers settle like dust on a quiet surface. Sleep, traveller. The cosmos continues to exhale, and we listen one spectrum at a time. Traveller to understand. 3I Atlas. We must examine one of the most debated observational features associated with it, the temporary appearance of a jet pointing toward the sun. It is important to approach this subject by removing dramatization and speculation, and relying strictly on the data gathered from telescopes in August and September 2025. The phenomenon is real, documented in imaging and spectroscopy, especially from the Keck Observatory, and yet the implications of this jet have often been misunderstood outside of scientific circles. This section focuses on what is known, what is measurable, and what is ruled out. To begin, we should establish a basic reference point under normal physical conditions. Cometary jets, dust tails, and ion tails almost always point away from the sun. Solar radiation pressure and solar wind apply force on dust and gas, pushing them outward. This rule is stable and widely observed. In tens of thousands of comet observations, the anti-solar orientation is consistent. when Atlas produced a narrow sunward-facing jet approximately 10,000 kilometers long, it naturally drew attention because it deviated from this common pattern. The Keck Observatory recorded this feature in late August 2025. The jet was not extremely bright, not broad, and not indicative of high energy. It was simply a narrow, detectable emission of material whose apparent direction when projected onto the observer's viewpoint aligned toward the sun rather than away from it. The scientific response was not panic or speculation. Instead, 3 conventional explanations were immediately considered. All 3 are grounded in known comet behavior. 1. Rotation-driven jet geometry. Comet nuclei often have irregular surfaces, asymmetric vents, and uneven thermal profiles. If a jet is emitted from a part of the nucleus that is oriented toward the sun, at the moment of measurement the ejected material will initially travel in that direction, before solar radiation pressure has enough time to redirect it. This effect is observed in several comets that possess deep cavities or strong localized vents. The jet does not defy physics, it simply emerges from a region temporarily facing the sun. 2. High mass dust particles in the outflow. If the jet contains dust grains that are heavier or larger than typical cometary dust, their inertia can temporarily overcome solar radiation pressure, making the jet appear to move sunward for a short distance. This does not require exotic materials. Comets have produced such heavy grain jets before, though not frequently. The key point is that solar radiation pressure acts more effectively on fine dust. Large grains behave differently during the first kilometers of ejection. 3. Line of sight projection effects. This may be the most straightforward explanation. Observations of comet jets depend heavily on the viewing angle from Earth. A jet that is actually pointed at a diagonal angle, say 20 degree or 30 degrees from the anti-solar direction, can appear sunward when projected into 2 dimensions. The geometry during the Keck observations, combined with the relative positions of Earth, Atlas and the Sun, made this a credible and mathematically consistent explanation. Projection errors are common when viewing faint elongated structures in space. In early September, the jet diminished and eventually disappeared from imaging data. This is not surprising. Cometary jets are transient, dependent on volatile pockets near the surface. Once a vent exhausts its volatile material or rotates into shadow, the activity stops. This behavior matches standard comet dynamics. The next question, the one that matters scientifically, is whether this jet had any measurable effect on Atlas's trajectory. If the jet had acted as a source of propulsion, even a small one, astronomers would detect deviations in the hyperbolic orbit. Comets do experience non-gravitational accelerations caused by asymmetric outgassing, but these accelerations are typically small and predictable. A sunward jet, if sufficiently strong, would produce a recoil force away from the sun, affecting position measurements. However, nothing of the sort was observed. Every high-precision measurement of 3i Atlas's motion, including astrometric data from ground-based observatories, orbit solutions provided by JPL, and comparisons of pre-jet and post-jet positions, shows the same result. The comet's trajectory did not change. There was no anomalous acceleration, no measurable deviation, no curve in the hyperbolic path beyond what gravitational forces predict. This point is essential. In orbital mechanics, even extremely small accelerations on the order of millimeters per second can accumulate over weeks into detectable deflections. Astronomers monitor these variations closely because even small non-gravitational forces can alter predictions. With Atlas, the data did not show any deviations. The hyperbola remained consistent. The object behaved like a comet under the influence of gravity alone. Some observers, hearing that a jet pointed toward the sun, imagined something akin to propulsion. But in physics, jet direction does not equal thrust direction. The force on the nucleus is opposite the mass outflow. Even if the jet had been strong, its recoil would have been anti-sunward and not sunward. Thus, the jet's visual orientation has no direct relationship to propulsion. More importantly, the outflow was low energy and faint. Nothing about it suggests an impulse capable of altering a multi-billion-ton nucleus. As Atlas continued inward along its path, it entered a new phase of activity driven by rising solar heating. Water vapor outgassing increased dramatically around 1.5 AU, consistent with thermal conduction. reaching deeper subsurface ice layers. The burst was sharp, but again, this is normal behaviour for a comet with a stratified nucleus. The large release did not produce measurable changes in trajectory indicating the forces involved were symmetrical or too weak to produce significant non-gravitational acceleration. During this period, astronomers focused on two key features: the dust tail determined largely by solar radiation pressure and the ion tail driven by solar wind interactions. Both tails pointed away from the Sun in exactly the expected manner. Their behaviour further confirmed that the earlier sunward jet was not indicative of an overall directional reversal or sustained phenomenon. Additionally, spectroscopic measurements taken before and after the jet event showed no signs of artificial emission-controlled gas pulses or periodicity. The outflow spectrum remained consistent with natural volatile-driven activity. It is also important to reinforce that this sunward jet phenomenon did not repeat, did not intensify, and did not become a stable feature of the object. It appeared briefly, required no exotic explanation, and disappeared as the comet rotated and warmed. In summary, a sunward-facing jet was observed. The jet was week-short, lived, and explainable by standard physical mechanisms. No non-gravitational acceleration occurred. No orbital deviation was detected. No evidence suggests artificial origin or controlled thrust. All available data points to a natural comet experiencing asymmetric and transient outgassing under normal solar heating conditions. Traveller, this is the scientific reality. The jet was unusual in appearance, but not anomalous in physical consequence. It changed nothing about Atlas's motion. It provided no evidence of intentional design. It was a short-lived feature fully consistent with cometary physics once the geometry, rotation, and observational angle are accounted for. This is how science handles anomalies, by examining them thoroughly, ruling out what is impossible, testing what is unlikely, and documenting what is observed. In the case of 3I Atlas, the observations remained consistent with the natural interstellar comet behaving according to physical laws we understand. Traveller, everything that astronomers hoped to learn from 3I Atlas was expected to peak at one specific moment perihelion, the instant the object reached its closest point to the Sun. For comets, this moment is scientifically valuable because it exposes the nucleus to maximum heating, maximum sublimation, and often maximum structural stress. And yet for 3I Atlas, perihelion arrived with a complication that shaped the entire observation campaign. From Earth, the object was completely hidden. This was not a surprise. The orbital geometry had been calculated months earlier, but the consequences of that geometry were significant. On October 29, 2025, when Atlas reached approximately 1.36 astronomical units from the Sun, it passed directly behind the Sun from Earth's point of view. This alignment placed the comet inside the region of the sky overwhelmed by solar glare. No ground-based telescope could observe it. No Earth-orbiting telescope could track it. Even spacecraft positioned at angles similar to Earth's orbit were effectively blind to the object. For astronomers, this was both expected and frustrating. Perihelion is often the most illuminating phase of a comet's passage. Rising temperatures can reveal deeper layers of material, alter outgassing patterns, or induce rotational changes. In some cases, the thermal stress can cause fragmentation. These events contain valuable information about the internal structure of the object information that cannot be retrieved from distant observations before or after. But with Atlas eclipsed by the Sun, none of these processes could be monitored in real time. The geometry was simple. Earth-Sun and 3I Atlas aligned in such a way that the comet appeared only a few arc minutes from the solar limb. To observe Atlas under those circumstances, a telescope would need the ability to image extremely faint targets in the immediate vicinity of a star over 1 billion times brighter. No existing instrument has that capability at such a close solar elongation. Solar coronagraphs can block the Sun, but they are designed to detect structures in the solar corona, not faint interstellar comets passing behind it. Thus, the scientific community accepted the blackout as an unavoidable interval. The duration of the eclipse window was not long in near astronomical terms, roughly 8 days during which the object remained unobservable. But in terms of comet behaviour, 8 days near perihelion is long enough for substantial changes to occur. models of cometary activity indicate that sublimation rates peak within a narrow window around closest approach, and Atlas entered that zone precisely when observation was impossible. For this reason, astronomers built their predictive models carefully ahead of time, attempting to anticipate how the comet might behave during the blackout. Before perihelion, all available data pointed to a nucleus several kilometers in diameter, with highly active CO2-driven outgassing and layered sublimation patterns. The comet had already produced several episodes of increased activity as it crossed the inner solar system. These episodes were fully consistent with known thermal processes acting on a nucleus containing stratified volatile reservoirs. The expectation was that perihelion would intensify these processes. The coma would likely expand. Dust production would increase. The ion tail might lengthen under stronger solar wind conditions. Two broad categories of outcomes were considered. First is the comet would remain structurally intact. Most nuclei of similar size survive perihelion without breaking apart. Their mass provides stability. Thermal gradients form, but internal cohesion prevents catastrophic fragmentation. Astronomers assigned a high probability to this scenario for Atlas, based on the pre-perihelion brightness trends and thermal modelling. Second is the comet might undergo fragmentation. Although less likely, fragmentation is always a possibility for large interstellar comets, especially those that have spent billions of years in extremely cold environments. Cosmic ray processing microfractures and internal voids can weaken structural integrity. If heating penetrated deep enough, pressure could build and cause the nucleus to split into multiple pieces. Such fragmentation has been documented in both long-period comets and first-time visitors to the inner solar system. Without live data from the blackout period, astronomers could not determine which outcome occurred. Instead, they prepared for rapid post-eclipse tracking once Atlas re-emerged into view. The most important measurements upon reappearance would be astrometric. By pinpointing the comet's exact position and comparing it to predicted orbital solutions, scientists could determine whether any non-gravitational forces acted on Atlas during perihelion. Outgassing asymmetry can produce measurable deviations, but such deviations are typically small. A significant shift would indicate either a strong asymmetric jet or structural fragmentation. The observational strategy involved repeated imaging sessions to reduce positional uncertainty and refine orbital parameters. The second key measurement category would be photometric. A comet that experienced intense perihelion activity would likely brighten, produce a larger coma, or exhibit a more prominent tail. Fragmentation, if it occurred, would produce noticeable changes in brightness distribution. Monitoring the light curve across the first days after reappearance would show whether new volatile layers had been exposed. Spectroscopic analysis would also be essential. Changes in outgassing composition may indicate that the surface layers were removed, revealing deeper reservoirs of volatiles, or different chemical stratification. Tracking the ratio of water vapour to carbon dioxide, carbon monoxide and other species provides insight into the internal chemistry of the nucleus. In addition, scientists prepared to evaluate polarization data measurements of how light scatters off dust particles. Polarization can reveal changes in dust, size distribution, or composition, both of which can be altered by perihelion events. Atlas's unusually strong negative polarization was one of its early distinguishing features. If this property changed after perihelion, it would help clarify whether dust characteristics were depth-dependent. All of this work required international coordination. Because Atlas would emerge from behind the Sun on November 7, 2025, visibility windows would vary between hemispheres and observatories. Teams across multiple continents prepared synchronized observation plans to ensure continuous data coverage, maximizing the chances of detecting transient events such as renewed jet formation or rotational changes. Despite the blackout, astronomers were not left completely without indirect information. Spacecraft positioned far from Earth offered different viewing angles, though none had a clear line of sight during the exact moment of perihelion. Some would resume observations earlier than Earth-based telescopes, providing partial constraints. But direct imaging remained impossible until the comet moved safely away from the Sun's glare. Throughout this period, one question consistently arose: whether perihelion could reveal any sign of non-natural behaviour in the object. From the data available before the eclipse, there was no evidence to suggest artificial activity. The trajectory followed gravitational predictions precisely. The outgassing spectra matched volatile-driven sublimation. No anomalous accelerations were detected. Based on this consistent behaviour, astronomers anticipated a natural evolution through perihelion. The temporary lack of visibility did not imply that something unusual might occur, only that we would learn about perihelion effects retrospectively rather than in real time. This is not uncommon in astronomy. Many periodic comets pass behind the Sun during key phases of activity. Their behaviour is reconstructed from pre- and post-perihelion data, and the same method applies here. From a scientific standpoint, the blackout period was simply a gap in direct monitoring, not a source of uncertainty about the physical nature of Atlas. Models predicted natural outcomes based on established physics. After the eclipse, those predictions would be tested against observations. Traveller. This is the essence of the perihelion eclipse window, a predictable interval of limited visibility occurring at the moment of maximum thermal activity, requiring careful preparation and measured expectations. During these days, the comet continued along its path, responding to solar energy in ways governed by known physical laws. And when it emerged again, the instruments would resume their work, comparing models to reality, one measurement at a time. Astronomy is patient by necessity. The universe rarely offers uninterrupted visibility. Sometimes we wait. Sometimes we watch from afar. Sometimes we simply prepare and accept that processes occur beyond our view. The value lies in what we discover once the object returns to the observable sky. Observer, when an object passes behind the Sun, the universe offers a brief pause. The data stream stops, instruments fall silent, and all that remains is expectation. For 3i Atlas, this pause lasted only 8 days, but the significance of those 8 days was substantial. Every prediction about its future behaviour depended on what occurred during that hidden interval. And so, in early November, astronomers prepared for its return with the same careful patience that defines much of planetary science. November 7, 2025. That was the date when the geometry finally shifted. As Atlas moved along its hyperbolic path, it reached a position where sunlight no longer drowned its faint glow. On that morning, telescopes in both hemispheres were aligned, automated systems were primed, and observation campaigns activated the moment the comet crossed the threshold of visibility. For the first time since perihelion instruments could collect photons scattered from its coma and nucleus, reappearance is not merely the act of seeing an object again. In planetary astronomy, reappearance is an experiment. It allows scientists to compare the post-perihelion state of the object with the predictive models built before the eclipse. Any deviation in position, brightness, spectral line, strength, tail morphology, or coma structure contains information about the processes that occurred near the Sun. The first priority was precise astrometry. Observatories captured short exposures tracking background stars to establish reference frames with sub-arc second accuracy. These position measurements were fed into orbital determination software, which compared the comet's actual trajectory with the predicted path generated before the blackout. If Atlas had fragmented, the orbital solution would show increased scatter or multiple point sources. If asymmetric outgassing had produced non-gravitational forces, even subtle ones, the residuals in the orbital fit would reveal shifts. The initial results were consistent with expectations. The comet reappeared near its predicted coordinates within the uncertainties built into the model. This indicated that no large-scale fragmentation had occurred, at least not on the scale that would significantly alter the barycenter of the object. However small fragments, if present, might not be detectable immediately. Continued tracking over days and weeks would refine the solution and detect any delayed divergence. The second observational focus involved photometric measurements. By comparing brightness curves before and after perihelion, astronomers could determine how the activity level had changed. For comets, brightness is linked to the amount of gas and dust released from the nucleus, which in turn reflects thermal processes. Atlas had shown strong CO2-driven activity prior to perihelion. The expectation was that deeper layers would begin contributing vapour as solar heating penetrated further into the nucleus. Early photometry suggested an increase in coma size and overall brightness consistent with enhanced outgassing. This matched predictions for an object of Atlas's size and composition, especially one experiencing its first close pass through a solar system environment. As the object cooled, activity would gradually decline, but the immediate post-perihelion period is often the most dynamic. From this brightness, data scientists could also attempt to refine the rotation period. Before perihelion. Brightness variations hinted at possible rotational modulation, but the signal was weak and not easily isolated from activity noise. After perihelion, as the comet settled into a more stable emission pattern, clearer periodicity might appear. Any significant change in the rotation rate could indicate torque effects from asymmetric jets or structural shifts within the nucleus. The third major category of observation was spectroscopy, particularly from facilities equipped to capture infrared and ultraviolet emission lines. Spectroscopy provides details about the composition of gases in the coma. Prior to the eclipse, Atlas displayed an unusually high CO2 to water ratio, along with detections of carbon monoxide organic compounds and metals, including nickel and iron. Post-perihelion spectroscopy would show whether the exposed layers contained different volatile abundances. For example, an increase in water vapor relative to CO2 might indicate the erosion of CO2-rich surface layers, revealing water ice beneath. Alternatively, if CO2 remained dominant, it might suggest that the CO2-rich regions extended deeper into the nucleus than models predicted. Early spectra indicated continued CO2 richness, though analysis was ongoing. Instrument teams would refine the data over days and weeks, integrating multiple exposures to reduce noise and improve accuracy. Dust composition was also of interest. Atlas had displayed unusually strong negative polarization, suggesting small uniform or compositionally distinct dust grains. By measuring polarization angles after perihelion, scientists could assess whether deeper layers of dust differed from surface layers. If polarization became less negative, the dust composition might be more heterogeneous. If it remained strongly negative, the structure could be consistent throughout the nucleus. Another dimension of post-perihelion observation involved morphological changes to the tail and coma. Before perihelion, the comet had shown a sunward jet, and later, a transition to a standard anti-solar tail. After reappearance, astronomers monitored for new jets' asymmetries or streamers. These structures can reveal the orientation of active regions on the nucleus interactions with the solar wind and variations in dust grain size. Solar wind conditions near perihelion are dynamic, and changes in ion tail structure can provide indirect measurements of magnetic field fluctuations. Instruments observing from Earth, and later from spacecraft positioned elsewhere in the solar system, compared tail direction curvature and ion density patterns to models of solar wind behavior at that time. Complementing Earth-based data were observations from the Jupiter Icy Moons Explorer JUICE spacecraft. Though not positioned optimally for high-resolution imaging, JUICE had a sufficiently different line of sight to observe Atlas as it emerged from behind the Sun. This alternate angle allowed teams to triangulate coma morphology and refine three-dimensional models of the tail. Instruments on JUICE capable of detecting infrared absorption features provided early constraints on post-perihelion chemical changes. These spacecraft observations were not immediate. Data transmission constraints meant some results would arrive months later. Yet the knowledge that additional data sets were en route gave scientists confidence that the story of Atlas's perihelion passage would eventually be reconstructed with high fidelity. One of the more nuanced goals during reappearance involved searching for rotational breakup signatures. Cometary nuclei often develop structural weaknesses under thermal stress. If Atlas had experienced increased spin rate or uneven heating, cracks may have propagated across the nucleus. While major fragmentation would be evident, smaller-scale structural changes could be inferred through rotational modulation, jet periodicity or sudden brightness, changes unrelated to solar distance. Observatories continued gathering time series data across multiple nights, building detailed light curves. Subtle variations would accumulate into a clear rotational signature if present. Importantly, none of these observations were designed to test non-natural hypotheses. They were built around well-established cometary physics. If an object behaves naturally across all measurable domains, trajectory, chemistry, morphology, brightness, polarization, and rotation, then the simplest explanation remains the most reliable. Atlas's reappearance offered an opportunity to validate these expectations with fresh data. Over the next several days, the object continued to move outward from the Sun, cooling gradually returning to the thermal regime where activity declines. Ground-based facilities shifted from high-cadence monitoring to structured campaigns, gathering data during optimal weather and visibility conditions. Larger telescopes focused on spectroscopy and polarization, while smaller facilities tracked astrometry and brightness. By mid-November, the initial uncertainties surrounding perihelion had largely resolved. The nucleus was intact. The coma was expanded but consistent with model predictions. No anomalous acceleration appeared in the orbital solution. Chemical signatures fit natural processes. The dust polarization remained within the expected range for an interstellar object with Atlas's properties. The reappearance did not answer every question, but it clarified the most important one: the comet behaved consistently with natural processes throughout perihelion. The absence of anomalies was itself a data point reinforcing the interpretation that Atlas was a chemically unusual, yet physically ordinary interstellar comet. Observer, this is how planetary science proceeds. Not through dramatic revelations, but through quiet comparisons between prediction and observation. Through the steady accumulation of measurements, through careful, unhurried interpretation, reappearance was not an event to reveal extraordinary secrets. It was the moment when models met reality, and reality aligned calmly and consistently with the physics that govern all cometary bodies. Observer, whenever the scientific community encounters an object that defies familiar patterns, two parallel processes unfold. One is purely observational, concerned only with photons, trajectories, spectra, and data points. The other is interpretive, concerned with meaning. For 3I Atlas, the measurements themselves have remained steadily consistent with a natural comet, yet the interpretation has included an additional line of inquiry that, while unlikely, has been discussed seriously by a few researchers: whether an interstellar object could ever be artificial, and if so, how we would recognize it. This is not because the evidence around Atlas demands such an explanation, but because the question itself has scientific value. The artificial hypothesis began not as a claim, but as a methodological framework explored by scientists such as Dr. Avi Loeb of Harvard University. Loeb has argued that when dealing with rare cosmic visitors, we should consider even low probability possibilities if their implications are significant. His reasoning is simple: before ruling out the extraordinary, we must ensure that the ordinary has been fully examined. In his view, dismissing an artificial possibility without analysis risks overlooking what could be the most consequential discovery in human history. But the purpose is not to assume intention, it is to test whether any available data requires a non-natural explanation. When Loeb and his colleagues first evaluated Atlas, they identified several features that on their own were uncommon but still consistent with nature. Together, however, they were worth examining as a group. One such feature was the trajectory. Atlas approached the solar system with a trajectory inclined only 4.189 degrees from the ecliptic plane, the same plane in which most planets orbit. If interstellar objects arrive randomly from all directions, an approach this closely aligned is statistically unusual, approximately 0.2%. Additionally, the object happened to pass within 29 million kilometers of Mars, and later is projected to pass within 54 million kilometers of Jupiter. The probability of an interstellar object experiencing both encounters by chance is below 0.005%. These statistics do not imply design. Rare things happen naturally, but they were included as part of the larger discussion. Another feature that drew attention was the object's size. Atlas is several kilometers across, larger than the two previous confirmed interstellar visitors, Oumuamua and Borisov. If interstellar objects follow the same size distribution as comets in our solar system, then large objects should be far rarer than small ones. The fact that one of the first interstellar objects we detect is among the largest raises questions about observational bias formation environments and statistical expectations. Again, rarity does not indicate intention, but scientists note when expectations and observations diverge. A third point of interest was the geometry of perihelion. Atlas reached its closest point to the Sun while positioned directly behind the Sun, from Earth's perspective rendering it unobservable. during the period of maximum heating. In purely speculative models constructed only as intellectual exercises, researchers have considered whether a technological probe might time a maneuver to coincide with a period when Earth cannot observe it. These models do not suggest that Atlas performed such a maneuver. They merely illustrate a hypothetical behaviour pattern for artificial trajectories. The speculation was further fueled by early spectral measurements that detected nickel vapour but not iron, even though these metals usually appear together in nearly equal proportions in natural comets. Later observations did detect iron resolving most of the anomaly, but the initial imbalance prompted questions. The sunward jet observed prior to perihelion, a feature later explained as natural sublimation, also contributed to the list of unusual characteristics. None of these features required an artificial explanation, yet their combined rarity encouraged some researchers to treat the object as a valuable case study for refining the criteria by which we might identify non-natural behaviour in the future. Even so, the broader scientific community maintains a clear consensus every observation collected so far points toward a natural cometary origin. No evidence suggests propulsion, artificial structure, or engineered behaviour. Atlas has displayed no non-gravitational acceleration beyond what sublimation can explain. Its chemical spectrum, though unusual, falls within the range of possibilities for objects formed in cold, carbon-rich environments beyond our solar system. The dust polarization, while the most negative ever measured, reflects grain properties that could naturally arise in different planetary systems. The jet's coma evolution and rotational behaviour match the physics of volatile sublimation under solar heating. This is why most researchers reject the artificial hypothesis, not because it is unthinkable, but because the data does not require it. In planetary science, hypotheses are evaluated by necessity. Extraordinary explanations are not invoked when ordinary ones suffice. Yet Loeb's argument persists for a different reason. His position is not that Atlas is artificial, but that if humanity ever encounters an artificial interstellar object, we must have the intellectual tools to recognize it. Atlas provides an opportunity to test those tools. The debate reveals two philosophical approaches within science. One approach emphasizes parsimony. When an object behaves like a comet, looks like a comet, and matches known comet behavior, it should be classified as a comet unless evidence forces a different conclusion. The other approach emphasizes openness. When dealing with rare, unfamiliar phenomena, scientists should consider less likely hypotheses in parallel with likely ones. So long as those hypotheses are testable, both perspectives are important. One protects scientific rigor, the other guards against blind spots. The artificial hypothesis also raises methodological questions that extend beyond Atlas. What observable signs would distinguish a technological object from a natural one? Would it broadcast radio signals? Would it maintain a stable orientation inconsistent with tumbling physics? Would its trajectory reflect intentional maneuvers? Would its composition include refined metals, isotopic anomalies, or thermal signatures inconsistent with passive heating? None of these indicators appear in the data from Atlas, yet by articulating them, scientists refine the checklist that will guide future observations of interstellar visitors. Atlas has become a useful example, not because it is artificial, but because its unusual characteristics allow scientists to rehearse the process of hypothesis testing. Rare natural objects are essential for this kind of intellectual exercise. They challenge models and help define the edge cases, those points where nature surprises us and forces us to rethink our assumptions. Each anomaly once explained becomes another data point strengthening natural models. Each eliminated alternative narrows the conditions under which a truly artificial object might be recognized. What the reappearance of Atlas after perihelion confirmed is consistent. There were no unexpected accelerations, no structural signatures, no chemical indicators of artificial origin. Instead, Atlas behaved precisely as a large, volatile, rich, ancient comet would behave under intense solar heating. It maintained its predicted path within observational uncertainties. Its outgassing followed expected thermal gradients. Its dust production increased, then stabilized. Every measurement reaffirmed natural interpretation. Observer, the artificial hypothesis remains a scientific thought exercise rather than a conclusion. Its value lies in the clarity it brings when all evidence aligns with natural behavior, the simplest explanation remains the most reasonable, but the act of testing the hypothesis, the comparisons, the measurements, the skepticism, and the analysis strengthens the scientific process. It ensures that when future interstellar objects arrive, whether they resemble Atlas or differ from it entirely, we will approach them with the same balance of curiosity and discipline. In this sense, the debate around Atlas is not a disagreement about its nature. It is an exploration of how science should respond to the unexpected. It is a conversation about thresholds of evidence, about rarity and probability, about the distinction between what is possible and what is supported by data, and ultimately it is an expression of the humility that defines astronomy, the recognition that the universe is vast, that unusual does not mean unnatural, and that knowledge grows through careful observation rather than premature certainty. Atlas, in all its complexity, has served its purpose. It has reminded the scientific community that interpretation must remain flexible even when evidence is firm. It has highlighted the importance of frameworks for evaluating extraordinary claims, and it has demonstrated that interstellar visitors, even when unusual, are most often what they appear to be ancient remnants of distant star systems, shaped by time chemistry and gravity rather than intention. Listener, if an artificial interstellar object ever entered our solar system, the most important question astronomers would face is deceptively simple. How would we know? It is not enough to speculate about intention or design. In science, recognition must come from measurable, repeatable indicators, signatures that cannot be produced by natural processes. The discussion around 3i Atlas has brought this question into focus not because the object shows signs of technology, but because examining the criteria clarifies the difference between the extraordinary and the explainable. What emerges is not evidence of an artificial origin, but rather a framework for future discovery. The first and most fundamental diagnostic would be the detection of radio emissions. A technological probe, even a dormant or damaged one, might release waste heat or transmit signals within narrow frequency bands. Natural astronomical sources produce radio noise, but almost never structured patterns or modulated signals. For months, radio observatories pointed their instruments at Atlas, scanning across the spectrum for any sign of artificial communication. Nothing was detected. The object remained radio quiet in every observable frequency range. Silence in itself proves nothing natural. Comets are silent by nature. But if Atlas were broadcasting or receiving information, the instrument should have seen some anomaly. They did not. A second test involves trajectory. Natural objects move according to gravity, and in the case of comets, small non-gravitational forces produced by outgassing. These forces are predictable and can be modelled with high precision. Artificial objects would maneuver intentionally in ways that do not correspond to sublimation physics. Thousands of astrometric measurements were taken in the months before perihelion, and thousands more afterward. Each measurement placed Atlas precisely where gravity said it should be. There were no deviations, no unexplained accelerations, and no trajectory changes, inconsistent with a volatile, rich nucleus interacting with solar heat. The path remained clean and continuous. If a spacecraft were adjusting its course, even subtly, those motions would appear as residuals in the orbital solution. None appeared. Surface features offer another potential diagnostic. Natural objects exhibit irregular shapes, cratered surfaces, and chaotic textures shaped by impacts, sublimation, and rotation. Artificial objects might reveal geometric structures, symmetry, or reflectivity inconsistent with porous ice and dust. The closest images of Atlas, those captured during the Mars flyby by ESA and NASA spacecraft, showed only a faint unresolved coma. The high-resolution camera aboard the Mars Reconnaissance Orbiter, the one instrument capable of detecting coarse surface structure, has not yet released its data due to administrative delays unrelated to science. Even when those images become public, the object was too distant for meaningful surface imaging. At tens of millions of kilometers, no telescope can show structure finer than tens of kilometers. The absence of detail is a limitation of distance, not proof of natural origin, but it also prevents any argument for the artificial. Another diagnostic involves thermal signature. Artificial objects, especially those with energy systems or onboard electronics, radiate heat in ways that differ from passive ice under solar illumination. Infrared observations from the James Webb Space Telescope provided the most sensitive thermal measurements available. Atlas showed no infrared excess, no heat beyond what sunlight alone would produce. The thermal emissions matched expectations for a cold carbon-rich nucleus warming gradually as it approached the Sun. There was no evidence of internal power sources, reactors, or heat exchange systems. Composition offers yet another avenue for analysis. Natural objects form under specific chemical conditions determined by the protostellar disk they originate from. They contain volatiles, dust, and metals in ratios governed by astrophysics. Artificial objects would likely contain alloys, refined metals, or isotopic ratios inconsistent with known cosmic processes. Atlas has shown carbon dioxide, water, vapor, carbon monoxide, cyanogen, nickel, and iron, exactly the sorts of volatiles and metals expected in comets formed in extremely cold regions. The temporary absence of iron in early detections was intriguing, but later observations found it resolving the anomaly. The nickel emission was strong but consistent with scenarios involving nickel-bearing grains and carbon monoxide chemistry. No isotopic ratios beyond natural ranges were observed. Behavior is another test. Artificial objects might show abrupt changes, switch-like activity, sudden velocity shifts, deliberate orientation toward planets or spacecraft. Atlas showed increases in outgassing near perihelion, but those changes were gradual and matched models of thermal stress acting on a multi-layered nucleus. The sunward jet that appeared early in its approach changed into an anti-solar tail exactly when solar wind strength would naturally overpower the initial jet. Nothing in its behavior deviated from known dynamics. Some researchers consider long-term stability as a diagnostic. Natural comets fragment under stress, shed mass, or rotate irregularly. Artificial objects might be designed to resist such degradation. Atlas survived perihelion intact, but so do most large comets. The survival of a multi-kilometre nucleus is normal, not anomalous. More speculative diagnostics include attempts at communication, sending radar pulses or laser signals to see if an object responds. No such attempts have been made with Atlas, partly because the object shows no signs that would warrant such tests, and partly because any response would be highly unlikely even if the object were artificial. Yet the concept remains valuable. It defines the extremes of testability. Across all these metrics, radio emissions, trajectory, surface structure, thermal profile, composition, behavior, and long-term stability, Atlas satisfies natural explanations. It meets them in full, leaving no indicator that requires an artificial hypothesis. Yet the artificial hypothesis remains scientifically meaningful, not because Atlas fits it, but because thinking through the hypothesis clarifies how science should recognize the genuinely unusual. As detection capabilities increase, especially with forthcoming facilities like the Vera C, Rubin Observatory astronomers expect to discover many more interstellar objects. Some will look ordinary, some will challenge expectations, and perhaps one day one will resist natural interpretation even after all known physics has been applied. Preparing for that possibility is not fantasy, it is methodology. In the end, Observer 3i Atlas leaves us with something simple and steady, the reminder that discovery is not a destination but a posture, a way of looking at the universe with patience, honesty, and humility. We measured what we could measure, we questioned what deserved questioning, and we accepted what the evidence revealed. Atlas will continue its long, outward drift until it becomes just another faint traveller in a galaxy filled with billions like it. But for a brief moment it passed close enough for us to learn from it to challenge our assumptions, and to see our solar system not as the centre of anything, but as one quiet stop along an ancient galactic current. As it fades back into the dark, we are left not with certainty, but with something gentler and more enduring. The understanding that even the rarest visitors arrive bearing nothing more complicated than truth, carried in silence across the stars. And so, Traveller Our Time with 3i Atlas draws to a quiet close. Quiet. We followed this visitor from the moment it emerged out of darkness, traced its chemistry, its motion, its brief encounter with our sun. We asked our questions carefully, measured what could be measured, and allowed the rest to remain unforced. The universe rarely gives us certainty, but it always gives us enough to wonder. Now Atlas drifts outward again, cooling, dimming, returning to the deep where it has spent billions of years. we will not see it again. But the lessons it offered stay with us, that rare does not mean impossible, that the galaxy is full of places stranger and older than we can imagine, and that sometimes the simplest explanations carry the greatest truth. You watched with patience, observer. You listened without rushing to conclusions, and in doing so you practiced the oldest human instinct to look upward and let the unknown speak in its own language. Somewhere ahead of us, other wanderers are already moving through the dark, other fragments of distant worlds, other questions waiting for their moment to appear in our sky. The mystery continues as it always does, quiet, patient, unhurried. For now, let your thoughts settle like dust in starlight. Rest well, traveller. Stay curious. The universe will keep watch. If this story found you tonight, you may stay for the next.